Let's do another application of Bernoulli equation, and this time to an open channel flow. This picture shows a channel in which a liquid is flowing. There is an obstruction in the channel, and in this obstruction a cutout has been made of width B. The liquid flows out of that cutout such that it is till a height h above the crest of the cutout. We'll calculate the flow rate based on the value h and b. This is a typical picture of streamlines in such a flow. It would be quite complicated if we analyze like this, so we make a model. Let us assume that there is no drawdown and the liquid is coming out as a jet which is horizontal. Let us consider a streamline within this flow point 1 to 2. We assume that the width of the channel and height in the main channel is much larger than the height in the flow over the obstruction. So the velocity at point 1 can be considered to be much lower than the velocity at point 2. V1 is approximately 0. The pressure at point 1, if the velocities there are much smaller, then the pressure distribution vertically within the main channel can be considered to be hydrostatic, so that the gauge pressure at point 1 can be written as rho GH. The elevation Z1 is capital Y minus H, where capital Y is the total height of the flow in the channel, and H is the depth of point 1 from the free surface. Since the pressure below the jet and above the jet are both atmospheric, it is fair to assume that the pressure at point 2 is atmospheric. And then the Bernoulli equation is written simply as V1 square by twice G plus Z1 plus P1G divided by rho G is equal to capital Y minus H plus H is equal to capital Y. This is the evaluation at point 1. This would be also at the second point, equal to the velocity there is V2 square by twice G plus Y minus H plus Y. And so this would give you capital Y as evaluated before. So this gives you V2 is equal to under root twice G into H minus Y. This is the velocity at point 2. It varies with Y, the location of the point within the jet. This value is maximum when Y is equal to 0. That is at the bottommost point in the jet coming out, and this is minimum when Y is equal to capital H. We can assume the velocity there to be 0. We can find the discharge by considering the flow rate through this jet of width B, height capital H. We consider a small slice of thickness dy at height y. We have obtained the velocity v2 here. So discharge through this slice is dq is equal to v2 times the area, which is b dy. And to find out the total discharge, we integrate this from y is equal to 0 to y is equal to capital H, and we find out to be twice b by 3 under root twice g into h raised to power 3 by 2. So if I know b, and if I can measure the value of capital H, the height up to which the liquid flows above the crest of this obstruction, we can find out the flow rate. This is a method used in the actual field measurement of the flow through channels. For example, in this channel, an obstruction is created, a vertical scale is erected so that 0 of this coincides with the base of the cutout here in this obstruction. So the water flowing there, we measure the level, and this measurement is capital H. If we know the width b, using this equation, q dot is equal to cd times twice b by 3 under root twice g into h raised to power 3 by 2, we can measure the discharge rate. cd is called the discharge coefficient, and this discharge coefficient is actually a factor of ignorance. There are a lot of assumptions that were made in deriving this formula. So CD is an experimentally determined coefficient that corrects for those assumptions. For an actual channel, the CD varies with the height ratio HP and the width ratio B by capital B in this manner. So for each such measuring weir that we construct, we have a calibration chart, a discharge coefficient chart, and by measuring capital H and lowercase b and finding from this the discharge coefficient, we can find out the actual discharge. This is only one design of a measuring weir. For the flow, we can have a triangular weir like shown in this picture. We can do exactly similar calculations, and we can find out that the flow rate in this case is given by CD into 8 by 15 under the root twice g h raised to the power 5 tangent alpha by 2, where alpha is the angle of the V through which the flow takes place. This weir plate has been directly calibrated into discharge rate. Here, the flow rate is proportional to h raised to the power 5 by 2 as against h raised to the power 3 by 2 in rectangular notch that we saw in the last example. These are the typical discharge coefficients for a 90 degrees notch.